Collision frequency is the frequency, or it is defined as, it is the highest or maximum frequency with which a wave can reflect back towards the atmosphere or towards the ground surface with a vertical incidence. So it is considered as highest or maximum frequency with which a wave can reflect back. Means the other meaning of that is, listen, it means that beyond that critical frequency no wave will reflect back towards Earth's surface. Means it will refract. Means you will not get the received signal, means reflected signal back on the Earth's surface. But we don't want that. Is it not? So more than critical frequency we should not maintain any frequency. That type of frequency is called as critical frequency. But there is a constraint. That means there is one point that beyond critical frequency also some waves could able to reflect back to the ground surface. How? My point is, first point is critical frequency definition. Critical frequency is the highest frequency or maximum amount of frequency with which a wave traveling can reflect back towards Earth's surface from the ionospheric region. Okay? Means from the definition we can tell that that is the highest possible frequency or maximum frequency for a layer in ionosphere. Okay? Means beyond which, if suppose for a wave or for a layer 8.3 megahertz is the critical frequency, 8.4 megahertz frequency signal will refract, but it will not reflect back. But some waves with some frequencies more than critical frequency also could able to reflect back. How that can be possible? Anybody? How that can be possible? Do you understand my question? Try. Anybody? Listen. That depends on angle of incidence, because always refractive index of a layer in an ionosphere depends on both angle of reflection and angle of incidence. Okay? Here we are talking about reflection, but we are not talking about angle of incidence. If angle of incidence made larger, sufficient to reach the wave can reflect back towards the Earth's surface, up to that value, up to that angle of incidence, it can reflect back. But if a saturation point comes between angle of incidence and critical frequency, all the signals will refract, but it will not reflect back. That frequency is called as critical frequency, and we will represent critical frequency with Fc, and it is given by 9 root Nm. Fc is equal to 9 root Nm. What is Nm? What is Nm? Maximum electron concentration or electron density. Maximum electron density is nothing but Nm here. Okay? So for different layers we will have different critical frequencies, because Nm is not constant for all the layers in an ionosphere. First of all, let me clarify you one more point, that in an ionosphere we will have these many layers. In ionosphere we will have D layer, E layer, F1 layer and F2 layer, and D layer ranges from 50 to 90 kilometers above the Earth's surface, and E layer ranges from 90 to 140 km, and F1 layer 140 to 250 kilometers, and this one 250 to 400 kilometers above the earth's surface. 110 km is center and 220 km is center, means exact. You see, we will discuss now some properties of ionosphere briefly. Ionosphere is divided into 4 regions: D region, E region, F1 region and F2 region, or D layer, E layer, F1 layer and F2 layer. D layer ranges from 50 kilometers to 90 kilometers above the earth's surface. 50 to 90 kilometers above the earth's surface, and E layer ranges between 90 to 140 kilometers above the earth's surface, and most prominent part of E layer, most important part of E layer is concentrated at 110 kilometers above the earth's surface. Okay, and F1 layer ranges between 140 to 250 kilometers, and the most prominent part of F1 layer is concentrated at 220 kilometers above the earth's surface, and F2 layer ranges between 250 kilometers to 400 kilometers above the earth's surface. Clear? And during daytime we will have only 2 regions. During daytime we can find out only 2 regions. Sorry, during daytime we can find out only 3 regions: D, E, F. F1, F2 layers will combine, and during night time we will find out, we can analyze only 2 regions. Those 2 are E layer and F layer. That's all. There is no D region, there is no F1, F2 subdivision even. During night time you will have only 2. Those 2 are E layer and F layer. F1, F2 will combine then also. During night time also F1, F2 will combine, and we will call that as F layer and E layer. Only these 2 are responsible for communication. Not visible or not there means they will be there, but they are not responsible for our antenna communication or signal processing. They are not responsible during night time. Not responsible means, again, not totally responsible, but their role is less during night when compared to morning, daytime. That is the meaning there. Okay, means during night time that layer, entire layer will disappear, and during daytime that layer suddenly will come. No, that is not its meaning. Okay, its meaning is that it will have less prominence or less importance during night time, and it will have more importance during daytime. Clear? These layers are named after Appleton. One scientist name is Appleton. He found everything, means D layer, E layer, F1 layer, F2 layer. In the name of him, they have named these regions as D, E, F1 and F2, but I don't find any single letter related to these 4 letters, but they have named like that. Okay, so all these regions, why I told this point while we are discussing critical frequency is, D layer will have some amount of NM, ionic concentration or electron concentration we can say, or electron charge density we can say. Okay, and E layer will have different density, F1 layer will have different density, F2 layer will have different density. So critical frequency for each layer or for each region is different. It is not constant for all the ionospheric region. For D layer critical frequency is different, for E layer different, like that for F1 and F2. Is it clear? Is it clear? Now we have discussed another point, that if angle of incidence is more, then critical frequency will also changes. So for that condition should be satisfied is mu m is equal to sin Im, where mu m is refractive index, Im is maximum incident angle, So if this condition is satisfied, If this condition is satisfied, then we can change or we can have another critical frequency for a particular layer depending on again Nm. This must depends on Nm, no doubt in that, but this also depends on incident angle. If suppose this one satisfies, then beyond that frequency also some signals will transmit through that layer. So reflection is also possible beyond critical frequency. Mu m is equal to sin Im condition is satisfied. Clear? Clear to all? Please copy those two equations, and these DE, F1, F2 also you please copy. Now for a wave with some frequency which is greater than critical frequency, for a wave with some frequency which is greater than critical frequency to be reflected back, we must check another condition, that sin I should be greater than root over 1 minus fc square by f square, where fc is critical frequency, f is operating frequency. Please try to analyze this point. We are discussing that, or I told that one point, beyond critical frequency also some frequencies can reflect back. Beyond critical frequency some frequencies can reflect back. Which frequencies? How to find out that frequency? From this expression you can find out that amount of or that frequency. Okay, this condition must be satisfied, and besides this you have to, if you want to find out that frequency, which frequency can reflect back, which is beyond critical frequency, that you can find out from this expression. Sin I greater than root over 1 minus fc square by f square, where fc is 9 root nm critical frequency, means fc square is equal to 81 nm. Okay, so from this expression you can find out that frequency exactly even. Clear? Clear or not? Okay. Next one is collision frequency. Collision frequency. Collision. Please listen. Collision frequency means very simple. In atmosphere, whether it is ionosphere or stratosphere or troposphere, whatever it is, mostly in ionosphere, always collisions will take place between ions, heavy ions and electrons or charged particles. Always collisions will take place because of infinite number of reasons. One reason we can tell, because of variations in climatic conditions. Another reason, because of so much dust particles which we are producing. Okay, because of so many reasons there are always some amount of collision will be there between the particles. These collisions will destroy the actual momentum of the charged particles, whether they are electrons or protons or neutrons or neutral ions, whatever it is. They will destroy, these collisions will destroy the natural momentum of the charged particles. So that destruction of momentum will take place at one particular frequency for one particular layer. That frequency is called as collision frequency. That frequency is called as collision frequency. As is the previous case, this collision frequency will also vary from layer to layer. And one more important thing is, we must calculate the refractive index of the layer, and then we have to calculate the collision frequency of that particular layer. If you want to calculate collision frequency for that particular layer, you must know what is refractive index of that layer. So, write down, in the ionosphere, collisions always occur collisions always occur due to the presence of large number of electrons, neutral ions, neutral atoms and heavy ions. Some frictional loss of energy takes place due to the inelastic collisions collision of oscillations of electrons in the ionosphere. We will represent collision frequency as V and can be written as, V is equal to EE multiplied V minus j omega by m into V square plus omega square. Where all these parameters you know, I think. What is E? Small e? Charge of the electron, capital E. Electric field intensity, V. Velocity of electron, omega. Angular frequency, 2 pi f, m. Mass of the electron. Okay. So to calculate collision frequency, we need electric field intensity, velocity of the charged particle, mass of the charged particle and charge of the charged particle and frequency of operation. Then we can calculate collision frequency for a particular layer in the ionosphere. Clear? Is it clear or any doubt? Clear? Clear to all? Next one is virtual height. Listen, here two conditions are there. If we want to analyze virtual height, we have to take two conditions. Those two are earth is curved in nature. Second condition is earth is assumed to be flat. Earth is assumed to be flat, earth is curved in nature. In general, we will take earth as flat surface. This one only. Okay. So this is case 1 for us, this is case 2 for us. Okay. Like that we will analyze. And whether it is case 1 or case 2, distance between transmitter and receiver is same. Distance between transmitter and receiver is same because radius of earth is very large. If radius of earth is small, then there is definitely a difference between first case and second case. Definitely there will be some difference between these two. But because radius of earth, what is radius of earth? R. What is radius of earth? (6370 km), is it? 6370 km. Okay, approximately 6,370 kilometers, just radius of earth. So we can tell that there is no much difference between 1 and 2. Okay, that is another case. Now in fact, this is ionospheric region and this is earth surface. In ionospheric region, layer may be D or E or F1 or F2, whatever it is. The basic nature of ionospheric layer is it will reflect the signal back to earth surface. Whatever signal is coming to earth's ionosphere, it will try to reflect back. So obviously this transmitted signal will have this type of path. Okay, but actual path, this is expected path, means we will analyze the path like this, but actual path is not like this. Actual path will be like this, because at one point it will get reflection, at one particular point it will get reflection. That particular point we will not take into consideration because that distance is very less when compared to this distance is very less. So that's why we will not consider this. But in fact, for exact measurements we must consider actual path of the signal. So this is actual path of the signal. This is generally analyzed path. Okay. Now this height is called as virtual height, or in fact more clearly this height is called as virtual height of the layer. Okay, and this height is h. Generally we will represent this as h and virtual height as h dash. Do you understand now what is virtual height? In general, electromagnetic wave will travel through ionosphere by reflecting back into the earth surface. Okay, its path is assumed to be in this way, or its path will be in this direction. But in general, at one particular point only it will get reflection. At one particular point only it will get reflection. So that particular point we have to find out, then we can find out virtual height of the layer. Because after entering into layer, just it will not have a spherical path, it will have a clear cut cone type path. Because after reaching at one point it will have refractive index difference. Refractive index difference when is coming, at that point only it will reflect back. So that point is this, in fact. But this point we will analyze generally, because that is all, means the entire ionospheric region, everything is an ionospheric region. We will just assume this as the path, but this is the original path. Is it clear now? Is it clear now? So this is called as virtual height. Virtual height means its name only suggesting that it is not actual height. Virtually we can assume that as virtual height. Is it clear? And virtual height we can find out from this expression. Virtual height is equal to C multiplied T by 2. C multiplied T by 2. So what is C and what is T? Anybody? C is circumference, T you know temperature, or any other option? C is not circumference, C is velocity of light. C is velocity of light and T is time taken to travel a signal from transmitter to receiver. Time taken by the signal to travel from transmitter to the receiver. Okay, that is T. H dash is equal to C multiplied T divided by 2. Then D is equal to 2H by tan beta. D is equal to 2H by tan beta, where beta is equal to 90 minus alpha, where alpha is this and theta is this. Where alpha is this and theta is this. D, distance between transmitter and receiver. Distance between transmitter and receiver is D is equal to 2H by tan beta. Beta is equal to 90 minus alpha. Alpha you can analyze from the figure. Okay, angle between antenna and the propagated signal with respect to ground surface. Angle between antenna and the transmitted signal with respect to ground surface, assuming ground as a flat earth surface, a flat surface or else. Okay, so 2H by tan beta. H you know already, height. Clear? And theta is angle of elevation. You can find out angle of elevation from an expression that is given by 90 degrees minus beta minus sine inverse of theta is elevation angle or angle of elevation. Theta is angle of elevation, and we can find out directly angle of theta, angle of elevation from this expression 90 minus beta minus sine inverse of r cos beta by r plus h, where r is radius of earth and it is approximately equal to 6370 kilometers. Over. Now you please read these three topics just for 1 minute you read, 2 minutes you read. If you have any doubt you please ask me. Inelastic collisions and elastic collisions. In fact, inelastic collisions and elastic collisions is not concerned to our topic. Okay, I will let you know about that in the next class, because here point of interest is only collisions will occur. For us, collisions will occur, and that collisions, because of that, or that collisions are responsible at particular frequency for a particular layer. That's all important for us. Okay, we will discuss that in the next class. Next one is maximum usable frequency. Maximum usable frequency. Maximum usable frequency. Listen, in one case or in one sense, maximum usable frequency is also approximately equal to critical frequency, but it is different in one nature, that maximum usable frequency can be defined as MUF. We will define maximum usable frequency or MUF as it is the maximum possible frequency with which a wave can reflect back for a given distance, and for a given ionospheric layer. There, critical frequency, we will not discuss about distance, but we will discuss about particular layer, no doubt in that. Whereas while we are discussing maximum usable frequency, we must discuss about distance and particular layer. Distance means what? Which distance? From the ground surface, how much above, or what is the distance for that layer, particular layer, that distance, for that particular distance and for a particular layer. Here distance means another point also, means 2 points we have to consider. Those two distances are, means whichever is applicable we have to use that one. Another distance is distance between transmitter and receiver. Distance between transmitter and receiver, or distance of the specific region above the earth surface, or depending on the specific layer or specific region above the earth surface. We have to define maximum usable frequency. Maximum usable frequency, and beyond maximum usable frequency there is no frequency with which a wave can reflect back. But with the critical frequency, beyond critical frequency also a wave can reflect back. That is the only difference between maximum usable frequency and critical frequency. Do you understand clearly? These two are very confusing topics. Critical frequency and MUF, maximum usable frequency. Both are related to refractive index of the layer and incident angle and reflection angle. On these three, these two will depend. Both critical angle and critical frequency and maximum usable frequency. Then how to find out the difference? First thing is critical frequency. While we are discussing critical frequency, we should not bother about the distance factor. For a particular layer, critical frequency is this much, we can find out. And beyond critical frequency, some frequencies will exist if angle of incident satisfies one condition, some condition. That condition I have given, you can check that. Now coming to maximum usable frequency, it is defined as the maximum possible amount of frequency with which a wave can reflect back from the ionosphere for a given distance. For a given distance for a particular ionospheric layer. So here either distance between transmitter and receiver are important, or distance of the layer above the earth surface is important, or specific layer is important, which is there in common in two, critical frequency and maximum usable frequency. One more important point is beyond maximum usable frequency, no frequency will exist. Exist means no signal can reflect back. Beyond maximum usable frequency, no signal will reflect back. It will refract or it will penetrate through the ionosphere or beyond the ionosphere. It will penetrate but it will not reflect back. Whereas with critical frequency, more than critical frequency signal can also reflect back if it satisfies some conditions. That type of conditions are not there for maximum usable frequency. Is it clear? Is it clear to all? MUF. Now MUF range is between 8 megahertz to 35 megahertz. Generally maximum usable frequency ranges between 8 megahertz to 35 megahertz. And the expression for MUF is FC multiplied secant I, means 1 by cos I, where I is incident angle. I is incident angle or angle of incidence. FC is FC is what? Critical frequency. Critical frequency. Listen, this expression is applicable for 1000 kilometers distance only. This expression, maximum usable frequency, is applicable for 1000 kilometers distance only. If suppose distance is more than 1000 kilometers, then you can calculate maximum usable frequency like this, 3.4 into FC, where 3.4 is secant 74, means 74 degrees is the limiting angle of incidence. 74 degrees is the limiting angle of incidence beyond which we cannot have angle of incidence. 75 degrees, 76 degrees, 80 degrees or 90 degrees angle of incidence we will not have. Means with that communication is not possible. So that's why 74 degrees is the limiting angle of incidence. For incident angle, limiting angle is 74 degrees. So if distance is beyond 1000 kilometers, you can tell maximum usable frequency as 3.4 FC, where FC is critical frequency again. Is it clear?